In this video, we will talk about how to determine if a set of vectors is linearly independent. So here's the formal definition. Given vectors u1 through uk, we can say that they are linearly independent only if the equation a1 times u1 plus plus ak times uk is equal to 0 has the trivial solution. In other words, a1 is equal to 0, a2 is equal to 0. All of these up to ak are all equal to 0. So that's a bit of a mouthful, but I'm going to walk through two examples in this video of one set of vectors that is linearly independent, and in the second example I'll show you a set of vectors that is not linearly independent. So let's say we have these four vectors right here, and we want to know, are they linearly independent? Well, what we can do is we can place them all in one augmented matrix in which the augmented column has the values 0, 0, 0, 0, so all zeros. And what we can do is then convert that matrix to row echelon form and see what the solutions are to the equation. So let's write that. So let's say our augmented matrix will be, the first column will have the values from u1, the second column will have the values from u2, the third column will have the values from u3, the fourth column will have the values from u4, and as we said, the augmented column will just have all zeros. So we need to convert this matrix to row echelon form. And recall, if we have a pivot entry right here, or in other words, the first non-zero value in this row, we want all values below the pivot entry to be 0. So we need to make this 1 a 0, and we need to make this 2 a 0. So how can we do that? Well, notice we could just do row 2 minus row 1, because 1 minus 1, that would make a 0. And then here in row 3, we could do row 3 minus 2 times row 1, because that would be 2 minus 2, which is 0. So let's do that. So let's say row 2 is going to become row 2 minus row 1, and row 3 is going to become row 3 minus 2 times row 1. So let's see what we get. So the first row doesn't change, so I'll just rewrite those values. All right, the new row 2 is row 2 minus row 1. So 1 minus 1, that's 0. 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 2 is 1. And 0 minus 0 is 0. In row 3, we have row 3 minus 2 times row 1. So 2 minus 2 times 1, that's 0. 1 minus 2 times 0, that's just 1. 3 minus 2 times 1, so 3 minus 2, that's 1. And 7 minus 2 times 2. So 2 times 2 is 4, so 7 minus 4 is 3. And here we have 0 minus 2 times 0, that stays at 0. And row 4 didn't change at all, so we'll just rewrite those values. Okay, so here's our first pivot entry. Here's our second pivot entry. Remember, we want all the values below the pivot entries to be 0. So we got to make both of these 0. Okay, so I'm going to rewrite this matrix over here and make a little room. Okay, so to make this one a 0, we could just say row 3 minus row 2, because that would be 1 minus 1, which is 0. To make this one a 0, we could do the same thing, row 4 minus row 2. That would make a 0. So let's say row 3 will become row 3 minus row 2, and row 4 will become row 4 minus row 2. So here's what that looks like. The first row doesn't change at all, so we'll just rewrite those values. And the second row doesn't change at all, so we'll rewrite those values. Now row 3 is row 3 minus row 2. So 0 minus 0 is 0. 1 minus 1 is 0. 1 minus 1 is 0. 3 minus 1 is 2. 0 minus 0 is 0. Now row 4, we have row 4 minus row 2. So 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 1 is 1. 1 minus 1 is 0. And 0 minus 0 is 0. Okay, so the last step to get this in row echelon form is we want all of the pivots to be to the right of all pivots above them. So notice that if we just switch row 3 and 4, then we could have a pivot right here and a pivot right here, which is what we want. So we'll say let's just swap row 3 and row 4. So here's what we get as our row echelon form. 1, 0, 1, 2. So these first two rows don't change at all. And then we're swapping row 3 and row 4. So row 3 now becomes what row 4 was. And row 4 becomes this. So this matrix is now in row echelon form. And we just need to see, is the only possible solution to this system of equations that this matrix represents, is the only possible solution the trivial solution? In other words, a1 is 0, a2 is 0, So let's make a little room and rewrite this over here. Okay, so here's our matrix in row echelon form. Okay, so if we were to write these values in terms of a system of linear equations with the coefficients a1 through ak, here's what that would look like. We would have 1 times a1, or in other words, just a1, plus 0 times a2, plus 1 times a3, plus 2 times a4 is equal to 0. The next row we would have 1 times a2, plus 1 times a3, plus 1 times a4 is equal to 0. In the third row, we would have just a3 is equal to 0. And in the last row, we would have 2 times a4 is equal to 0. So if we wanted to solve for a1 through a4, let's start from the bottom here. 2 times a4 is equal to 0. That means a4 has to be equal to 0, because 2 multiplied by some number, this number has to be a 0 in order for this left-hand side to be 0. So a4 is 0. In row 3, here we have a3 is equal to 0, so that's just a3 is equal to 0. Now, if a3 and a4 are equal to 0, what does a2 have to be for this equation to be true? Well, a2 would also have to be 0. And lastly, we found a4 is 0, a3 is 0, so a1 would also have to be 0 for this equation to be true. So we can see that the only solution to this system of equations is the trivial solution, or in other words, all of the coefficients a1 through a4 have to be equal to 0. So that is the definition of what vectors are linearly independent. So we would say, yes, vectors u1, u2, u3, and u4 are linearly independent, because the only solution to this equation turned out to be the trivial solution. In other words, a1 through ak were all equal to 0. So these vectors are linearly independent. All right, let's check out our second example. Let's say we have these 3 vectors, and we want to know if they are linearly independent. So we'll use the same process as the last example, where we place all of these vectors into an augmented matrix, in which the augmented column has all 0 values, and then we'll convert the matrix to row echelon form. So here's what that matrix would look like. The first column is the values in u1, so 1, 1, 0. The second column is the values from u2. The third column are the values from u3. And the augmented column has all 0 values. So how can we convert this matrix to row echelon form? Well, here's our first pivot entry, and remember, we want all values below it to be 0. So how can we make this 1 a 0? Well, we could just do row 2 minus row 1. So let's do that. So let's say row 2 is going to become row 2 minus row 1. So row 1 doesn't change at all. We'll just rewrite those values. Now row 2 becomes 1 minus 1, which is 0. 3 minus 1, which is 2. 4 minus 0 is 4. 0 minus 0 is 0. And then we'll rewrite the third row since we didn't change that at all. Okay, so here's our first pivot entry. Here's our second pivot entry. Remember, we want all values below the pivot entries to be 0. So we need to make this 1 a 0. So how could we do that? We could say 2 times row 3 minus row 2, because that would be 2 minus 2, which is 0. So we'll say the new row 3 is going to be 2 times row 3 minus row 2. So here's what that would look like. The first row doesn't change at all. And the second row doesn't change at all. Now the third row is 2 times 0 minus 0, that's 0. 2 times 1 is 2, minus 2 is 0. 2 times 2 is 4, minus 4 is 0. And 2 times 0 minus 0 is just 0. So this matrix is in row echelon form. And we want to know, what are the solutions to this matrix? So I'm going to rewrite this matrix over here and make a little room. So if we were to write the values of this row echelon form matrix in terms of a1 through ak, here's what that would look like. The first row would be 1 times a1 plus 1 times a2 plus 0 times a3 is equal to 0. The second row would be 2 times a2 plus 4 times a3 is 0. And notice in this last row, we have all zeros. So in other words, we could just say that a3 is just equal to itself. Or in other words, it's allowed to be anything. And what we'll find is that we can choose any value for a3, and we'll be able to solve for a2 and a1. So for example, let's just say a3 is equal to 1. If A3 is equal to 1, then in this equation we would have 4 times 1, let's solve that, 2A2 plus 4 is equal to 0. So if we subtract a 4, we'll get 2A2 is equal to negative 4. If we divide by 2 on each side, A2 would be equal to negative 2. And then knowing that, we can solve for A1 up here. So we have A1 minus 2 is 0. A1 must be equal to 2. So notice, we just found values for A1, A2, and A3 that satisfy the equation A1 times U1 plus A2 times U2 plus A3 times U3 is equal to 0. So since we found values that solve this equation and A1, A2, and A3 are not all equal to 0, that means that these vectors are not linearly independent. Or another way to say that is that they are linearly dependent. And one hack that you can kind of use is when you convert this matrix to row echelon form, if there's a free variable, that's a dead giveaway that the vectors are not linearly independent. So notice that the first column has a pivot entry, the second column has a pivot entry, but the third column does not have a pivot entry. So we would say the first variable and the second variable are both pivot variables, but this third column represents a free variable. So if there's a free variable, then the vectors cannot be linearly independent. And as a side note, we would say that this system of equations actually has an infinite number of solutions because we can pick any value that we want for A3 and we would be able to solve for A2 and A1. So in this example, we picked A3 to be 1, but if we picked, say, A3 to be 10, we could also solve for A2 and A1 and we could find another solution to this equation in which A1, A2, and A3 are not all 0. So keep that in mind. So as our final answer for this one, we're going to write U1, U2, U3 are linearly dependent.